Hi everyone, today is November 15th, 2013 and is my 52nd birthday, and as a gift to everyone I would like to share everything that I have so far found with my research on reactive power. And we'll be doing an experiment here to see the benefit of using reactive power, for instance, in a generator. So here we have a variac that's hooked up to the 120 volt 60 hertz grid, and there I have a power meter which will take in consideration the power factor and give a output in watts. And as you see now, there is actually 4 watts being consumed just with the variac connected, with nothing happening. And we also have here, for those who wish to look into things much closer, a current sensing resistor attached to the scope probes, and that's a 0.1 ohm, so 0.1 ohm, and we have the probe set up in the configuration to measure voltage against current, and so we can also be looking at phase, and that's going to this plug here, which is going to an induction motor, and we'll get to that. And here I've got another meter that's set on AC, and we're going to be measuring the voltage across this resistor, and it's pure sine wave that's coming out. So this meter here will be very accurate. I've checked it out, and this is a true RMS meter, and since it's pure sine wave, it'll be fine. We have a 1 k ohm resistor here, and this wire here is connected to a generator, which was a gasoline generator, which I've converted to basically electric. So there's the alternator head that used to be connected to a gasoline engine, which I've removed. And to do these tests, I used this small induction motor, and you might recognize this motor in other tests maybe that I've done. It's a 6-inch bench grinder, and it's again 120 volt 60 hertz motor. And here on this shaft here I have a reflective strip here, so that I can check the RPM out with my optical reader. There might be a little bit of noise when I start this because I wasn't able to perfectly align the 2 shafts together here. They're just really epoxied together because this generator head only has a bearing here at the back. It was relying on the front end just on the bearing on the gasoline motor. So now I'm having to have that shaft holding to this internal shaft of the alternator. But anyways, it works just for this test. And basically the test will be to look at what this generator can do in normal set configuration, in this configuration with a load attached to it at a certain RPM and a certain amount of current going into it. And then I'm going to set up a reactive circuit, which then will compare to see how much the input is compared to standard and with the reactive circuit. And again, as well on the output, also reactive circuit there, and we'll see if it changes if the reactive circuit creates a load to the generator. So I don't know if some of you are familiar with reactive power, but I've been researching it for a while now, and what I'm going to be giving away here is a lot of work. It represents many months of work and a lot of experiments. And I've actually checked on the internet and I cannot find anything that would confirm if a reactive circuit or something that's operating on reactive power, if you connect it to a generator, will it cause a load to the generator? In this case we have an alternator because it's an AC generator. So I don't know if you understand that, but that's very important. This is a crucial question, and nowhere on the internet could I get a confirmation of this in writing, or could I find a video of somebody who has done this test. So today I'm going to be doing this test, and you will see what the results are. And they might be a little different than what you might think. I've been going over this with people that are quite qualified in the field, and they would tell me it doesn't matter if the circuit is reactive, it has to put a load on the generator, or the alternator in this case. So this is what we're going to check and see. So now I'll just start the induction motor here. I've got to give it a spin to get it going. So now we see the current here in yellow coming up, and I've got the math function on the oscilloscope there as well to display. Now we see here we're consuming the watts, and that will drop down as the RPM increases. So now, use my tachometer here and try to get a reading. So 2,870 RPM. I have a switch here which is off, so the load is not being fed yet by the generator. We are consuming 98 watts, and there is the data here on the input voltage, and there is the data on the current present going through the current sensing resistor, and there is our waveform. So current is in phase with voltage, and the math here is indicating that because it's all going on this side above. Alright, so we're again in our wattage around the 97 watts, and I will flick the switch now, and now we have about 54 volts. I'm going to raise my variac here just a touch. I want to bring it close to 57 volts and see what we get. Close enough. Okay. Well, I won't be able to. There's a fluctuation right now in the voltage, so it takes very little to change things. So that's about as good as I'll get right now. So we're using 101 watts at 56 volts on the load, and I'm going to switch it off. Nothing, and you hear the generator increasing in RPM, and you see our wattage dropping. We're at 98, 97 watts. Alright, I'll flick it back on. You hear our generator dropping, which is normal. Okay, we're back at 56, and we're back at 101 watts. So basically, the resistor here is outputting a little more than 3 watts. I've done the calculation. With 56 volts, you've got a little over 3 watts. And as you see, when I turn it on and off, there's fluctuations in the voltage, but we're basically using 3 watts. I'll turn it off right now, and there you go. So we have a 3 watts difference, and the meter is showing it clearly. I'll do it once more. I'll go on. The load is on. Alright, and our RPM has dropped. Sorry about that. So 100 and 102 watts, 56 volts on our resistor. I switch it off, nothing, you hear the RPM go up and the wattage goes down. Well, I mean, I'm having fluctuations with the voltage, so it changes a little bit. I'll turn it on again. Load is on. There you go. So we're up to 107. That's because of the fluctuations in the voltage. Okay? So now look at your voltage there, and there is the current. Maybe I'll just leave that there, and I'll switch it off, and you can see the current drop. It's off now. Now it's back on. Now it's off. Now I'll post these on the public forum, and there's a link to that on the bottom of this video. Okay, so now the next step is I'm going to set up a reactive circuit here on the output and try to get the same 56 volts on the resistor there, and we're going to be looking at that next. So basically a reactive current to find out if that gives us any benefit on a load while a generator is operating. And like I say, there is no such experiment or test that's available on a video that I have seen or anybody could find, because I've asked, or even written information to confirm this. So as far as I'm concerned, this is fairly important and could lead to possible very efficient generators. Okay, so here we have the reactive circuit that I have been developing, and what it is, it's a microwave oven transformer and a capacitor that is in series on the primary of the microwave oven transformer, and the load is connected to the, or the resistor, the load is connected to the secondary as the output. So right now the generator obviously is not functioning, and this circuit is very efficient, and we can produce the same amount of voltage on that resistor with much less RPM. So you will notice that the motor takes less RPM. So I'm going to start it up. I'll let that find its RPM. And right now you can even see that it's starting up at a lower wattage because I have the voltage down lower on the variac, but eventually it's going to take off and find its speed. So here we can have a look at the scope shot again, and I'll show you the voltage information there. So that's the voltage range that we're going to be working with. and that, well, the current, we can't get that until we've reached maximum RPM. So it's starting to wind up now. So at about 2,700 RPM. It's now reached its plateau. And now you can have a look again at the current. And there is the voltage. And this is the amount of watts that we're using. So we're able to drop down watts because we're using less voltage, because this circuit is very efficient. Now let's flick the switch and see if this creates a load on the generator. So I've turned the switch on, and if we look, we're producing 55 volts here on our resistor, and I can raise that a little touch. It's very sensitive to get an exact reading there. There we go. I'm trying to adjust the variac here, but it's just such a minute amount. We have just some small fluctuations. Anyways, I'm pretty close there. That's pretty well what we had on the other resistor. I can raise it up higher, I don't even care, because basically it makes no load to the generator. So we'll leave it there. So we got now actually more. We got 58 volts on our resistor, and let's have a look here at our RPM. So we're at 2732. So we definitely have not lost RPM. We have 58 volts more than what we had on the standard test, and we're using 85 watts. And there is our voltage, and there is the current. Okay, so now what I'll do is I'll just switch off the load, or the reactive circuit. Did you see a difference? I'll turn it back on. Turn it off. Here we can look at the watt meter. It's off. Now I'll turn it on. No change. Producing 58 volts. Turn it off. No drop. 0 volts. So there you go. A reactive circuit will not create a load to a generator. You could produce power without really paying for it. Basically, the current is circulating through the circuit and coming back. That's what reactive power is. But you have to know how to set the phase. Your phase has to be very close to 90 degrees between the difference between the current and voltage. Right now, this is what our motor is using. So right now our voltage and current are pretty much in phase. When you're 90 degrees out of phase, your current would be more like right here in the middle between the voltage phase. So the next step is going to be to add, so we have a reactive circuit on this side here, which is helping our output to get basically far as I would be concerned, that would be free energy because you're not paying for it. You click it on, you hear an effect, a little kind of a hit to the generator, but because the circuit is just sending back what it's used and it's storing its power in the, I guess, in the magnetic flux in that transformer and giving you some real power for free. So the next step now would be to use a reactive circuit here between the variac and the induction motor to see if we can now also drop the amount of current that is going to that induction motor. So that will be the next test. Okay, now we're back, and we have a reactive circuit here on the output, and now I have a reactive circuit on the input. And the idea here is to see if that will actually also reduce our power consumption. So right now the load isn't on, and the circuit is tuned and running so that we have the same RPM. Let's check our RPM here. So 2,700 RPM, exactly what we had previously. And the big difference though is that now we have this reactive circuit, which is some capacitors, a certain value of capacitors here. We've got 10 microfarad, 18 and 8 added up, and those capacitors here are in series with the primary of another microwave oven transformer. And on the secondary of the microwave oven transformer, I have another set of high voltage capacitors. These are rated well over 1,000 volts, and they're 0.22 microfarad each. So you've got a total of about 0.26 microfarad there. They're in parallel. And so that's connected on the secondary. And there you go. And then that's, so the primary, our current here from the variac is going in this capacitor bank, just like starts in series. It goes one side of this primary and out the other side to our induction motor that's turning it at 5,700 RPM. So prior, when we did our test with just the output here, we had about 100 watts that was needed for the induction motor to turn our load prior that we had this reactive circuit. So right now what we've done here on the input is going to also reduce our current to turn the motor at the same RPM. And there you go. We are now using 50 watts to turn that motor at the same RPM. So there's another benefit here again. And the reason why we have that benefit is, if you look here, there is our current in yellow, and in green here is our voltage. And you can see that now they are out of phase. Now it's not quite 90 degrees out of phase, because it's obviously showing that we're using some power here, 50 watts. And but if we can get this actually at 90 degrees out of phase, basically this will be 0. And if this is 0, then you can attach this to a generator, and the generator will output the energy into the circuit without cost of load onto the generator, as you've seen here. So I hope you're following me here where all this is going, because this is important. So phase shift is everything, and that's what you want to get. And you seem, from what my experiments are, you seem to need to be using transformers to do that. And there are transformers on a Valley device, and I believe this is what he's doing, and that's how I kind of noticed that that's what he's doing, and understood it because I had already been working on this for quite a while now. So there you go, it's turning, and let's apply our load. I'm going to switch that on here. So as you hear a slap into the motor here, but I assure you the voltage has not, or the current is not asking for any more current for doing that. So we've got 59 volts here on our 1K ohm load, and if you look at the wattage, it's not asking for anything more. And if we take our RPM reading, we've not lost anything. Okay, so again the same thing, and we're outputting even more on our 1K ohm resistor there, and we're only using, looks like 49 watts at this time. And that's thanks to this, and this is what you want to achieve. And you can see now the math at the back here on red is actually dropping down. And the more you get the math to drop down, if the math can be equal at the top and the bottom, you're basically just using power and returning it. And if you can get work out of that, good for you. That would be the secret to a device being very, very efficient. So there is the information on our voltage. So as you can see, the voltage is much higher now. So we have to input more voltage, but voltage is cheap, doesn't cost anything. Here's our current. So if you do the math, you will find that our 50 watts there is pretty accurate. So right now what I'll do is I'll shut the circuit off. Okay, the circuit is off now, and I'll switch it back on. Okay, now outputting 59 volts on the 1K ohm resistor. I don't know if you saw any change on the current. It's off. Now the big thing too is, notice here is our phase shift is not shifting at all. Totally steady. And that's thanks to what I've done here with that microwave oven transformer on the input. Putting these capacitors on the high impedance secondary seems to really stabilize the primary, and that's the secret. And what I'm giving away here is quite a bit. I don't know if you realize that, but I believe this would lead to a loop generator. Now what I'm using here is all stuff I had on hand. And I don't have the money that this individual Valley has to get a really efficient generator. He's using a permanent magnet alternator. This is not a permanent magnet alternator, and it needs high RPM to start producing energy. That's why we're not outputting very much. But if I had something efficient like he has, you can see him in one video, he just turns the shaft and it makes a 2,000 watt grinder start to turn right away. And again, this induction motor is very small and not very powerful, and I'm sure his induction motor is a lot more efficient than that. So I don't think it would take very much to make this device loop. Obviously it probably would take a bigger transformer, and you can see on his device he has a much bigger transformer than that. I don't know if you've noticed that he even has a transformer on his device, but yes, he does. So there you go. I think I'm giving away a lot here, and I hope you do appreciate it, and we'll be, I'll be continuing to do this work. I've got a few ideas of other things that I can do to see if I can close the loop, but this is the basic fundamentals of how the Valley device works, and there's another individual that has another device that you can see transformers on as well that is claiming that it's looped as well. And I believe those two devices could possibly be real because of what I am seeing here. So that's about all that I have to share. And thanks for watching. Bye now.